Okay, yeah, yeah. We're getting closer. We're getting closer. No, it's okay. Don't worry about it. Yep. I'd like to apologize to everybody. I thought the talk was at 5 o'clock until 6 instead of 4 o'clock until 5. But we'll be ready to go in just a second. I think this is the one. Yes. Okay. Oops. What happened? Oh, there it is. Let's try it again. Okay. This is kind of a talk, it's a kind of retrospective of the time that I've been in computers, and we're going to go through back in time a little bit, and then we're going to go forward in time a little bit to see the types of things that keep me awake at night. So I'm going to give a warning because the history that I'm going to give is going to be from my memory, and sometimes my memory isn't the best in the world, and sometimes it's twisted because I see it the way that I see things. I'm sure that Mr. Gates sees things the way that he sees things, and Mr. Jobs, if he was alive, would see things even a different way. So, if you don't want to listen, you can leave. I'm not insulted. So, I've been in computers a long time, since 1969. I've had a wide variety of different jobs, but most of the time I've been using either a UNIX system or, in the last 20 years, a Linux system. And I've had many different jobs: programmers, systems administrators, marketing managers. I've worked for small companies and large ones. And I've been both a customer, waiting for that patch, waiting for that fix, waiting for that extension, and I've been a vendor trying to produce that patch, that fix, or that extension for my customers. So, a lot of people have only known computers since the time of what I call the computer store. But before the computer store, computers were so large and so expensive that if you wanted to go to a store and buy one, you would need an 18-wheel tractor-trailer truck to go and haul it home. You need a 20-ton air conditioner to cool it, and particularly in Brazil, because you're so close to the equator. And you would need 3-phase electrical power to plug it in. In fact, you might have to build Itaipu next to you just to power it. They were slow by our standards. They were logically small by our standards. That particular one right there, that computer, is an IBM 1130. That is the first computer I ever programmed on, and I programmed in shrink wrap. Now, most of the software that was distributed in those days was distributed in source code format because there wasn't enough of any one type of computer to be able to justify creating a binary package to distribute the software. And so people just gave you the source code, and if you played with it enough, you could get it to work on your computer. If you did order a piece of commercial software, such as a commercial compiler, a lot of times you would pay perhaps 100,000 US dollars for it, and along with the 9-inch magnetic tape that the compiler came on, you would actually have an engineer show up. And that engineer's job was to put the source code for the compiler on your machine and assemble it, and later on compile it again and again until the thing actually worked. And if it didn't work, the engineer would actually fix it. Now, this philosophy actually existed quite late in computer science. There was a company called Evans and Sutherland that made really great graphics boards. And their graphics boards would cost almost as much as the whole computer system. And their graphics boards would drive huge displays used for things like airplane trainers, things like that. And each and every one of their boards came with a circuit diagram that showed the components on the board. If one of their boards broke, they would send a field technician out to the customer site with an oscilloscope and a soldering iron, and they would actually trace through the board and change the board to fix the problem. Of course, this created a slight problem for the software, because the hardware was no longer what the software people expected. And so there had to be a special version of the software made for them, too. And this is the type of thing. This was happening in 1986. But in the period between 1943 and 1977, most of the software was written in source code form. And most of the people who wrote the software were not professional programmers. They were writing software for themselves, not for somebody else. That may have been the only thing they did for their company was write software, but they were writing software for a particular purpose. And if you were a physicist, you wrote software to help you do physics. If you were a chemist, you wrote software to do chemistry. And a lot of these customers would write the software, and then they would say, what am I going to do with it? It's software that's good, it's helpful to me, but I don't want to sell it because it's hard to sell software. When you sell software, you have to promise people that you're going to fix bugs. You have to write documentation so that people know how your software works. You have to do fairly good quality and testing across different operating systems. And that was not what these people did. So a lot of them contributed their software to some type of user group. Digital Equipment Corporation had DECUS, the Digital Equipment Corporation User Society. And they had a library. You would contribute your software to it. You would write a little abstract about what your software did. And they would print a catalog of the software and what computer systems it ran on. And so I, as a college student, would look through the catalog, find a piece of software I liked that ran on one of our computers, and I would send away perhaps $5 to buy it. And then I would, show it to my friends and my roommates, or things like that, and they might also buy a piece of software, or I could just duplicate it for them, because in those days, software was not protected by copyright, nor was software protected by patents. And in any case, these people didn't care. The people that wrote this didn't care. They were happy that somebody else was using their software. And sometimes you would go to a DECUS meeting and you would meet one of these people. And you say, oh man, that software was really good. I had some ideas that would improve it. And the person would say, well, send me these ideas and I'll work it into the code. Or, because you had the source code, you could show them what you did. And they'd say, oh, thank you, let me have a copy of that tape. Sometimes you went to these people and said, hey, it was a really great program. I don't have any suggestions about how to change it, but let me buy you a beer. but let me buy you dinner. Or how would you like to work for my company? And all of these, of course, are reasons why we write free software today. We need it for ourselves. We don't want to give support to it necessarily because it's a lot of work and it's not what we do. When you have other people using it, you may be able to get improvements from them. Now, in 1969, a strange thing happened. Two people in New Jersey decided to write this little operating system called UNIX. Now, up until that time, operating systems were written for one specific purpose: to help the customer use the hardware better. Because without an operating system, you run one program at a time. And between the time that the first program runs and the second program starts, that machine is idle. It's not doing anything. And when you pay $2.5 million for a machine, and you have a staff of people who are operating it, when the machine is idle, it's no fun. So by putting an operating system on there, you can start to have multiple programs running at the same time. And so when one program finishes, the other ones take over. You could also have better utilization of your peripheral devices, your printers, your card readers, things like that. Because without the operating system, the program says print, and then the CPU just sits there waiting for the line printer to print. The program says read a card, and the computer sits there waiting for the slow card reader to pull in the card. But with an operating system, you read all the cards in to the disk, which is much faster than the card reader. And when you print to a file, so you're not tying up your program. But Unix was the first operating system that said, you know, the hardware is becoming cheaper. And maybe what we should be doing is creating a portable operating system. This is my phone telling me it's time to go to get ready to go to the talk. Pardon me while I shut it off. There we go. Power off. So Unix was an operating system that said, look, the hardware is becoming cheaper, and maybe what we should be preserving is the programmer's time. We should be preserving the user's time and expertise. We should be making it so that it's the same operating system across all these different pieces of hardware. And you don't have to write a different program because it's a time-sharing system, or a batch system, or a physics system, or a chemical system. And then one more thing happened in 1969. Linus Torvalds was born, and we'll see more about him later. Now, in 1977 to 83, this is where programs like CP/M came in. CP/M was an operating system that ran on 8088s and Z80 computers, things like that. The Apple II started up, the IBM PC, and the price of computing dropped again. People started to manufacture these pieces of hardware, and a company up in Redmond, Washington said, maybe we can manufacture the software like people manufacture cookie cutters. Make one for everybody. And at first, some of the hobbyists tended to try and keep the computer marketplace free as in open. And they would take source code for the programs and put it up on bulletin boards that people could then download it, type it in, see how it worked. But after a while, more and more companies started to produce binary-only software. And the people that were used to getting the software in source code became used to getting the software in binary-only code. Now, let me give you an example of why this is really bad. I actually bought a piece of binary code back in that time frame. I got it on 2 8-inch floppy disks. And I paid $1,000 for this software. And one day I found a bug in it. So I called up the company, which is very close to my house, and I got the president of the company on the line because the company only had 100 employees. And they had about 1,000 customers. So when the telephone rang, I got the president on the line. I told him what my problem was. He says, "Oh yeah, I know what that problem is." And he could say that because he was the chief programmer. He says, "You know, I think we could fix that problem today and get it through quality assurance and have it in the post tomorrow." And he could say that because he was the head of quality assurance and he was the head shipping clerk. And sure enough, the next day, I got 2 8-inch floppy disks in the mail, and it fixed my problem. And if each one of the 1,000 customers turned in 2 problem reports each year, that's 2,000 reports going to the 100 engineers, that's 20 reports per engineer. And they have a year to do it. It's no problem to fix 20 reports. But let's just say it's today. They've expanded a little bit. They have 150 engineers, but they have 4.5 million customers. You don't pay $1,000 for the software anymore. That's the good news. You only pay $10 for it. But if each one of those customers puts in 2 problem reports, that's 9 million pieces of paper going to these 150 engineers every year. That's 60,000 problem reports per engineer. And of course, some of those problem reports are duplicates of each other, but it's still an overwhelming amount of work. And this is why when you call up the little company today, you no longer get the president of the company on the line, nor do you get the chief programmer, nor do you get the head of quality control, nor do you get the shipping clerk. What you get is, "Please press button number 1 for sales, button number 2 for support." So you press button number 2 and then you get music, music. And then you get disconnected. This is the problem. It's not because these people don't want to give you good service. They can't give you good service. It's impossible. And it's even less possible that they could do it and still be profitable as a company. Now I know there are some people in the free software space that the word profit is almost a curse word. That companies making money is something that they just don't like at all. But see, the opposite of a company making money is a company losing money. And if a company loses money too long, this is what happens. They lay off their people, so all these people lose their jobs, and then eventually the company goes bankrupt, and they don't exist anymore. So companies have to make money. And a lot of people in the free software space really don't understand how much money it takes to run even the smallest company. But it's a problem, and we have to fix it. There was one person, Richard Stallman, at the time an MIT student in 1984, who had gotten a piece of binary code he was trying to use, and he couldn't get it to work. And of course he couldn't fix it because it was binary-only code. And Richard was used to having code in source code form. And he objected to this, so he decided to form a project called GNU, which stands for GNU is not UNIX, a complete open source operating system, a complete operating system with the source code, and following certain laws and rules and principles, which we'll get to later. Also, during the same period, there was other projects going on, such as the University of California, Berkeley, creating the Berkeley software distribution, which eventually went into the BSDs, NetBSD, FreeBSD, and OpenBSD. There were other open source projects like SendMail, Bind, which became the basis of DNS, Postgres, which was the follow-on to a relational database called Ingress, and Postgres exists today as Postgres SQL. And at MIT, there was a thing called Project Athena, which gave us the X Windows system, Kerberos, and other technologies, and thousands of other technologies that were developed as what we call today free software. And after a while, everything was there, more or less, for this operating system, except the kernel. Now, why didn't Richard Stallman start with the kernel first? I mean, there was an interesting project developing a kernel. Why didn't he do that first? Well, if in 1984 he had developed the herd, by the time 2011 came around, nobody would care anymore. If he developed the kernel that early, it'd be so hopelessly out of date by the time he had the rest of the operating system done that nobody would care. And in the meantime, there would be no programs, no applications to run on it. So he took the opposite philosophy. He said, let me create an application that almost every programmer will use, and I'll make it run across all these different operating systems, even if they are closed source. And people will use it, and they'll understand the value of open source code. And so he wrote a version of Emacs. And some people say he could have stopped right there because Emacs is like an entire operating system. But he went on to do other things like create the compiler suite and shell utilities and things like that. So by 1991, almost everything was there except the kernel. And that was when a young man in Helsinki, Finland, had gotten a brand new 386 computer from his parents for Christmas. And he realized that the operating system that came with that wasn't able to take advantage of the architecture. Now, I'm going to ask you a question. You can shout out the answer if you know it. What was the thing in the 386 architecture that made it so unique? What? Not multitasking. We could do multitasking without that. You're getting close with real mode. You're getting close to 32 bits. Protected mode, we had that. Demand page virtual memory. Because the 286 did swapping. So you could have protected mode, but you couldn't have a process that was larger than the real memory. Okay? If you could by kind of cheating. You could do swapping of overlays to bring them in, but demand page virtual memory opened up a whole new realm of programming. And Linus knew that there were some UNIX systems that could do this. Now, why didn't Microsoft go in and make Windows do demand page virtual memory? It was because their customers were all still on 286s, 186s, 8088s, which did not support this. So Microsoft said, oh, our code will still work on a 386, it just won't take advantage of it. But Linus wanted something that would. And all of the Unix systems that he could find were either very expensive or they weren't really open. So he decided he was going to write his own, just for fun. This wasn't going to be a big project or anything like that. He was just going to do it as a hobby. And by 1993 and 94, various distributions were beginning to appear. Now, the interesting part about this was Linus didn't bring out a distribution. He just brought out a kernel. Other people went in and said, I'll take Linus's kernel, I'll take, the GNU tools, I'll take all these things and put them together. And so you had distributions like Soft Landing Systems, SLS, Yggdrasil, Transamerica. These don't exist anymore. They were a little bit before the time, and they weren't marketed properly, and consequently, they disappeared. But other distributions, like Slackware, and a small distribution which became known as Red Hat Software, started to appear too, and those have survived the test of time. And then, just about at the end of 1994, or at the beginning of 1994, version 1.0 of the kernel came out, and that's when I met Linus. I met Linus in May of 1994. He came to DECUS, the Digital Equipment Corporation Youth Society, that was being held in New Orleans. Now, the great thing about New Orleans is that it is one of the two adult Disneylands in the United States. One adult Disneyland is Las Vegas. In Las Vegas, you can gamble, you can have all sorts of interesting sexual adventures, and you can drink liquor on the street. In New Orleans, you can do all of those things and more. You can get almost everything you want in New Orleans and a lot of things you don't want. And I went to New Orleans, I saw Linux for the first time. I sat down, I used it. And it was like playing a wonderful piano. Because if you have a piano that's well tuned, you can usually get some pretty good music out of it. But if you have something like a Yamaha or another fine piano with all of the keys weighted, all of the key tops exactly even, then it's a joy to play that piano. And that's what Linux was like. If I thought of it as BSD, it was BSD. If I thought of it as System 5, it was System 5. And I said, Digital had just come out with the Alpha processor, a very fast CPU with 64-bit address space. Now, to give you an idea of what that means, if you have 32 bits, you can address 4 billion bytes of data at one time. But if you have 64 bits, you can address 4 billion times 4 billion bytes of data. That's so much data that if you were to fill up a 1 gigabyte disk every second of the day, every day of the year, you could fill up those disks for 5,386 years and still not run out of address space. Or you could store enough data, 128 bytes of data, for every square millimeter on the surface of the Earth, including all the oceans. It's a lot of data. And I wanted to do experimentation research with very large address spaces to see if we could speed up computation. At that time, there was only about 124,000 people using Linux. Today, actually that's an old number, it's probably in the billions that are using Linux in one way or the other. And I said to Linus, would you like to port Linux to the alpha so that you could have a 64-bit kernel and also get out the Intel-isms out of the kernel? Now, if somebody is out there who works for Intel, I'm not meaning this in a bad way. But the problem is, when programmers work on only one architecture, they tend to take shortcuts to make the operating system work faster, and they tie it to a particular architecture. And the problem with that is twofold. When you want to go to a new architecture, it means you have to change a lot of the things in the system. Or if the architecture changes from underneath of you, the company that made your chip takes out an instruction, then you have to go through the entire system to find out where that went wrong. And so by making your operating system portable, you can allow the compiler to make those changes for you. And you, as a programmer, don't have to worry as much about it. And Linus said, well, I've been trying to get... Oh, yeah, I'm going to be in trouble again. Yes, I've been trying to get a 64-bit system to do this with, and I've been looking at the digital alpha. But the people at Digital in Helsinki have been having a hard time getting me one. So I may have to do the PowerPC instead. I'm taking this off to protect the interpreters. Ah! I took off my earphone to protect the interpreters for that. But that was my response. And I dropped my drink that I was drinking on board the boat, on the deck of the boat, and I never, ever drop an alcoholic drink. And I told him not to do anything hasty, and in less than 1 week, I had an alpha processor headed to Helsinki, Finland. And it arrived 3 days before the IBM PowerPC. Linus didn't turn on the IBM PowerPC for a year after that because he was concentrating on the alpha. And after that, he turned on the PowerPC so he could tell IBM he had turned it on. We started the alpha port in earnest in June of 1994. Actually, at that time, I was shipping him documentation. He was studying how to do it. We started the project in earnest in January of 1995. And by November of 1995, Red Hat shipped an Alpha Linux version. I have been in the computing industry for 45 years. This was the fastest I had ever seen a port of an operating system from one architecture to the other, from 32-bit to 64, done by anybody. No company, no other company, no other group had ever done one faster. This is done by a group of people, for the most part, who never saw each other face to face, being done over the internet by a bunch of volunteers, so-called amateurs. Now, in that last sentence, I have just knocked down everything that Microsoft has ever said about Linux. Are these people amateurs? Yes. They were not being paid to do this. Do you know soccer players or football players that are maybe better than professionals, but they're playing for the fun, and they just don't get paid? Yes. Okay. It was amazing. And it showed me the power of the community. Now, about that same time frame, we in the computing community were having a problem. Supercomputer companies were going out of business. Companies like Cray and ECL and a bunch of others were becoming defunct. And two people at NASA, Dr. Thomas Sterling and Donald Becker, created a concept which they called Beowulf Systems. I don't know why they called it Beowulf, they just did. But what they did was take commodity off-the-shelf systems, we call them COTS, cheap PCs, and hook them together to do parallel programming. And they could produce the power of an IBM SP2 supercomputer for 1/40th of the cost. Or turning it around, for the same amount of money, they could give you a supercomputer that was 40 times faster than if you bought one from Cray or ECL. And all they were these common off-the-shelf components. Sometimes they were, in the early days, they were simply computer boxes put onto shelves, hooked together with Ethernet. Later on, they used special connects like MirrorNet and crossbar switches, but a lot of times it was just Ethernet. And they started to solve huge numbers of problems with them. They used software. They're looking for an operating system, and they chose GNU Linux. And they had libraries like PVM, Parallel Virtual Machine, MPI, Message Passing Interface, and OpenMP to handle the parallelism in the code. Over time, this was even extended to NUMA types of architectures. So what types of problems are we trying to solve? Image rendering problems. We'll get to those in a moment. Image recognition. Recently, there was a plane that was lost out at sea, and we had a lot of people looking for it. They could see the stuff floating down on the ocean from satellite images far up in space. Now, if human beings have to spend their lives looking at these pictures of these small areas of the ocean, after a while, they get tired. And there was a project where individual people could look at the web, and each one would look at a small piece of the ocean looking for some of this debris from the airplane. But most of the time what happens is you have computers doing that. And computers are looking at those places, and when they recognize something that's strange, they will call over a human so the human can look at it, because that little dot off the coast of Brazil might be the conning tower of a submarine that's about to launch a missile at you. Or it could simply be the sail of a sailboat with people having a holiday. Trust me, if you blow up a sailboat, it ruins your whole day. The paperwork alone is really bad. So computers can do that, and they can do other types of image recognition, such as looking for mammograms, checking out, see if a woman has cancer. Weather forecasting. We have known for the last 50 years how to tell with 100% accuracy whether it's going to rain in the next 24 hours. The problem is, it took us 48 hours to gather all the data and do the computation. So we could tell with 100% accuracy what the weather was going to be 24 hours ago. After using a lot of computer time. Or we could just hire a Boy Scout to stick their hand out the window. But as CPUs sped up, we could now predict 100% accuracy if it's raining right now, 100% accuracy if it's going to rain in the next 10 minutes, 100% accuracy if it's going to rain in the next 10 hours. Now, the 10-hour point is interesting because it means that you don't put the fuel into the rocket ship to take off. You don't put people's lives at jeopardy. You don't schedule your picnic, okay? All these things, if you can predict that, they can predict with 100% accuracy whether there's going to be an earthquake in Japan in the next 30 seconds. You say, mad dog? What's the use of that? You're so old and fat you can't even run to the door in 30 seconds. You're still going to be killed by the earthquake. The thing that does the most damage in an earthquake is not the earthquake itself, but the firestorm, the fires that happen after the earthquake, where the earthquake has ruptured the pipes bringing the natural gas, and the electrical lines fall, create the spark, and set off the fires. So now, what happens in Japan is 30 seconds before the earthquake, they turn off all the natural gas lines. They turn off the electricity. And then after the earthquake is over, they can decide when to turn it back on. 30 seconds gives you the time to lower the gate on the bridge, allow all the cars to get off of it before the earthquake happens. That's what 30 seconds can do. How many of you saw the movie Titanic? Rendered with 60 alpha processors over the course of a year. How many of you saw Lord of the Rings? Rendered with 1,024 Intel 64-bit processors over the course of a year. Why so many? Because we as human beings want to have more and more realistic computer-generated graphics all the time. And there's a rule of thumb that says the better the graphics, the more CPU you throw at it. But these systems are all done by Beowulf style of computers running GNU Linux. University of Sao Paulo, the first time I came to Brazil was 1996. And the University of Sao Paulo had been going to the High Performance Computing Conference for many years, winning prizes. I saw that they were creating real-time computer graphics using Beowulf Systems. And they also were doing image recognition of the mammograms taken on a woman's breast. They had reduced the time of figuring out whether the woman had breast cancer from 10 hours to 10 minutes. And this probably saved a good number of women's lives because they can go to her and say, I'm sorry, you have breast cancer, we need to schedule the operation, or we can't tell, we need to do some more tests. Now, also at that time, Linux didn't have very many applications for it. And of course, if you don't have many applications for an operating system, you don't have a lot of people using it. However, there was this thing happening about that time called the World Wide Web. And people were already using the internet with things like shell accounts and things like that. But mostly, they were Unix systems, typically from Sun, an operating system called Solaris, and Spark computer systems, which were a RISC-style system and pretty expensive. Linux allowed these same ISPs, Internet Service Providers, to be able to have a Unix system and run on cheap PCs for savings of about 30%. And it had all the things that the ISPs needed. It was stable, it was secure, it had all the features they were used to, and you had the source code. Why was that important? because these machines were in the very front of the internet. These were the machines that people were going to attack and try and break into, and if there was any hole in the machine, you needed to have it fixed right away. You could not wait for some vendor to create the patch. Now, I worked at Digital at the same time. We had an old operating system called Ultrix, which we had retired, just like Microsoft has retired XP. We had a new operating system called Digital UNIX. And when we found out that there was a particularly nasty problem, it took our engineers 2 weeks to figure out what the problem was, generate the patch, and send it out to our customers. So for 2 weeks, our customer systems were crashing all the time. The open source community had the same problem. It was generic across all Unix-like systems. But when they found out what the problem was, it took them 3 hours to generate the patch in source code and put it up on the net for everybody to use. 3 hours, 2 weeks. Which group got the better support? With our older system, Ultrix, my management was not going to generate a patch. They said, I'm sorry, we retired that system. I had to threaten them with blackmail to get them to generate that patch because there were people who were still using it, just like there are people who are still using XP. In 1998, databases started to do the port. Oracle, Informix, this was a big thing. This is like your parents smiling at you when you graduate from college. When databases ported their software, it meant that you were actually a real operating system and people were actually going to be using you for real work. And all of a sudden, the computing industry had new respect for Linux. I forgot to tell you, back in 1994 when I met Linus and decided to help him with this port, I came back to my company and put together a presentation about Linux. And my last bullet on my last slide said, Linux is inevitable. And my manager said, what do you mean by that? I said, it means that nobody's going to stop it. There's nothing that anybody can do. It's going to happen. And it's going to be very powerful, and it's going to be worth a lot of money to people in the future. And all of those people, all of my management laughed at me. And now all of my management work for Red Hat. And in October 1998, more companies started to sell support for Linux. In particular, one large company whose name rhymes with IBM. They said, yes, we're going to support Linux, and not only that, we're going to invest $1 billion into Linux. A year later, they said, not only did we remake that $1 billion, but we made another $1 billion. In the year 2000, people started to bring in embedded systems. Up until this time, embedded systems had different operating systems made by different companies for different chips. And hardly any of these operating systems had any type of networking stack to allow them to talk to other systems. But people were starting to demand that their systems talk to the internet. And so the companies said, oh, look, there's an operating system that already talks to the internet. It already works across a wide variety of different architectures. It already has all the compilers we need, and it's royalty-free. And so they chose Linux to do this. I love in particular this ATM machine. This is a fine example of where Linux really works and really shines. Because the bank that made this machine previously used an operating system called OS/2. It was an operating system from IBM that IBM just decided one day, we're not going to support it anymore. We're not going to port it to new architectures. We're not going to fix bugs. We're not going to do anything. And so this bank, which had a huge number of ATM machines that were 386s, 486s, low-end Pentiums, small amounts of memory, this bank decided to use Linux instead. And it was so successful that they put a little penguin on the front of every screen. 2 years ago, I was in Florianopolis. I saw one of their ATM machines, and the little penguin is still there. All sorts of embedded systems. This person right here, his name is Eric Troen. He's sitting on top of a robot made by a company called iRobot. Eric was one of 3 people that started Red Hat Software. And Eric is now a multimillionaire. All sorts of different types of embedded systems. This is a watch that was made as a prototype by IBM and Casio. My little laser point, oh, there we go. And it unfortunately never made it into mass production, but it was still an interesting example. And I challenge people to make these types of things. In March of 2000, .coms were beginning to fail, but in winter of 2003, Red Hat became profitable for the same time, at the same time. And last year, they had $1 billion year, $1 billion worth of money selling free software. In Curitiba, Brazil, there was a school that had no computers, but they went to all these banks that were getting new computers, asked them for the old ones, and created their own computing lab. So now we're coming to the age of Linux. We have to have Linux and free software in your military, in your government, because you need to be able to support this. You can't depend on some other country, some other place, to give you something as critical as software. You need to develop the skills to develop this software yourself. And it also helps with a balance of payments. Even though in Brazil you pirate 84% of your desktop software, you still ship several $billion worth of money to the United States and other places to pay for software that you could replace with free software. And that money that goes out of your country could stay here in your country, paying you to do programming. And when you do programming here in your country, you take your money and you buy local housing, local food, and pay local taxes. But when you send that money outside, there's only so much cachaça that Bill Gates is going to drink. So here we have the software Livre. And this last one is often the most contentious of all of the freedoms. The freedom to use the software for any reason. So let's take a look at this and see how it's going to both affect the problems we have in the future and the problems we have now. All of those companies up there, Enron, DEC, Kodak, Nortel, every single one of those were once the second largest or largest company in their field on the earth. And all of them went bankrupt within a 2-year span of time, leaving their customers without any way of maintaining their systems. So when people tell you that Microsoft will never go bankrupt, Just say Enron at them. Just say Kodak at them. We've seen the problem with privacy and NSA. It's actually much worse than that. You have to start developing inside of Brazil a culture of being able to audit both your software and your hardware to find out exactly what's going on with that. Because without that ability to audit that, to check it, to be able to see exactly what's going on, you're going to be at the mercy of the people who do make the hardware and software. Microsoft was seen as being a monopoly. They had 90% of the desktop market. Without free software, there was literally no way of penetrating that monopoly. You could not penetrate the monopoly by funding another company to try and go against it. It's very hard. Now, we have a problem. It's not all good news for us. We have a problem in fragmentation. And there's people who are confused by the number of different choices we give them. I'm not saying that fragmentation is bad. I'm saying that we have to be clearer in why we do our fragmentation and what people should be using. We need to be able to set up real standards like ODF and be able to explain why they are better than crappy standards like OOXML. We need to fight for net neutrality. There's a whole series of people who are trying to take away net neutrality. But we have to recognize that the more pornography we download, it has to be paid by somebody. And so if we want higher and higher bandwidth, we can't just demand this from our ISPs. We have to recognize that they need money to build up their infrastructure. We have to stop jobs moving to Taiwan, China, and the United States. We have to keep the money and the expertise here inside of Brazil so you can build your new future. I talked about bandwidth limitations already. We have to fight against complacency. We have to go out and continue to fight for free software. I'm 63 years old. I'm not going to be able to do this for the next 63 years. So it's going to have to be up to you. Recently, there's been articles about artificial intelligence and how computers are becoming smarter and smarter and mimicking the human mind. One of the things that keeps me up at night, two things actually. If we create an artificially intelligent computer, if we unplug it, is it murder? And secondly, if we create an artificially intelligent computer and allow some people to use it for what they want, such as creating new weapons, do we allow it to be a... something just went wrong. Do we allow it to have its own power supply? I have the strangest feeling that my power supply just went out. I don't think we, in our hurry to get this thing set up, I think my notebook has been running off of battery this whole time. And this may be the end of the talk. But I want to give you one last thought. Somebody today, or during this week, came up to me and said, Mad Dog, you're one of the most important people in free software. And I said, no, you're wrong. This is a community of people. We all work together. These last couple of problems we have is not just a problem of the technical people. Artificial intelligence is not just a matter of the technical people. We need to have the philosophers thinking about this too. What makes an artificially intelligent thing? What rights does that thing have when we create it? Now, this has been talked about for years in science fiction books and things like that. But we are drawing closer to that problem. But to the issue of whether Mad Dog is important to the free software community or not, I want you to do me a favor. Tomorrow morning, when you get up, go to the mirror and look into the mirror, and you will see the most important person in free software. Because it's you. All of you. And with all of you, that is why nobody can stop free software. Thank you very much.